Hi, I'm Simon MacMillan. I'm a staff scientist here at Science North and an astronomer, and today I want to talk to you about telescopes. So what I was just doing, looking through this telescope, that's what you might imagine an astronomer doing. We look through a telescope, look up at what's in the sky, and figure out what's going on. And actually that's not really what a lot of astronomers do anymore, but we'll get to that. And to start, I want to talk a little bit about why we actually use a telescope. So we have a lens here and a light comes through, and another lens at the back, and then a light comes out through the eyepiece. But why do we actually want to look through a telescope at the sky? Well, people usually think that it's all about magnification. We want to make things look bigger. And that's certainly part of it, but it's not the most important reason we use telescopes. The biggest reason is actually that we want to gather up as much light as we can to see very faint objects. And so we need a big lens here at the front to gather as much light as we can and concentrate it into our eyeball. And that's really the biggest reason. The other thing is that we want to see more detail. And that's different from magnification. That's the resolution. So think of an example, for example, like an image on your computer. Magnification is just if you blow up that image, you make the zoom bigger and bigger and bigger. It doesn't necessarily allow you to see a lot more detail at some point. It just gets fuzzy. The resolution is if those pixels that you actually have in your image are smaller and smaller and smaller. So the difference between, for example, an old-fashioned television and a modern TV, an HD TV, was much smaller pixels. It looks a lot crisper. And that's what astronomers are really after. So we're after a crisp image of a faint object far away. And the telescope allows us to get a higher resolution of very, very faint objects. And by choosing the right eyepiece, we can actually change the magnification, blow it up, make it look nice and big, but it's not the primary reason why we have telescopes. So the one I have here in front of me is called a refracting telescope. So we have a lens at the front and a lens at the back. And as I described, the light comes in, focuses through the eyepiece, and we can look through it. And that's how we started. That's how Galileo used a telescope like this to first start looking at the night sky. Now, that actually became pretty cumbersome after a while, because to make these telescopes bigger, you're going to build bigger lenses, which first of all is sort of challenging, make a nice accurate big lens, and they have to make them really, really, really long. So old telescopes sometimes were actually up to tens of meters long, really, really long. And that becomes a real challenge to actually just point that thing into the night sky. And the reason for that is that when you make a bigger lens, it actually starts to separate the colors, so they don't all focus in the same place. That's called aberration. The only way to make that better is to make the telescope really long. And that helped to keep the colors together in your final image. But it became a huge issue after a while. So we actually switched to a different type of telescope. So most modern telescopes are actually a variation on this kind of telescope here, a reflecting telescope. You can see inside that there's actually a mirror at the back that reflects the light that comes in. There's a little mirror at the front here, so the light reflects back to that one, and then that mirror sends it out the back through a hole, and you observe it at the back. This is called a reflecting telescope, and these ones you can make really, really huge. Like this example here, called the Large Binocular Telescope. There's two mirrors actually here that are about 8 meters across, and so now you can imagine you can gather up a lot of light with this telescope. You could never build a lens that big, but you can certainly build a mirror of this size, and that's really, most modern telescopes are a variation on that. So these telescopes really just cover a small part of the electromagnetic spectrum, but to learn the most we can from these little dots of light out in the night sky, we want to look at the whole spectrum, so not just visible light, but infrared and radio waves, ultraviolet, and even X-rays. So one example that I want to talk about a little bit is how we can observe the night sky with radio waves. So radio telescopes are actually huge. In this example here, we have the Green Bank telescope. It's about 100 meters across, and it looks like a big satellite dish, and it's sort of similar to that. The radio waves have very, very little energy compared to light waves, so you need a huge dish to actually collect enough light to get a good image, because these objects are very, very faint. So we built them really, really big. They don't have to be as accurate because radio waves are actually much longer. And so you can see a lot of different things at radio waves. So we can also make them really big by separating them out into multiple dishes. So you might have seen a picture like this before. This is the very large array, and here we have 27 antennas, and by combining them and moving them further and further apart, you can actually get higher and higher resolution. So in radio astronomy, we can improve our resolution, so that detail, that fine detail you see, by making the antennas work together and separating them far out into a plane or even across the whole Earth to observe the night sky. What kind of stuff do we see? Well, here we have an image of the Crab Nebula in visible light and some other wavelengths, and you can see this blue interior, which is hot gas from an exploding star. Around it you have cooler filaments of gas and dust, and you can see molecules, all different colors. So you can't see all of that in visible light. When you look in radio waves, the Crab Nebula looks very different. Now you see the widely distributed energy coming from electrons spiraling around magnetic fields. You could never see that invisible. You can also see some of the really cold gas that doesn't emit visible light but emits energy at much lower wavelengths, longer wavelengths. So as you can see, there's a wide variety of telescopes out there that we can use, including just a few that we have here. A lot of modern telescopes are now actually out in space, like the Hubble Space Telescope. That gets us above the atmosphere and above the clouds, and we don't have to worry about all that. And astronomers actually don't really look through telescopes a whole lot anymore. But it's still fun to do. We still like to do it here at Science North, and if you want to come and check out what the sky looks like through a telescope, you can come and join us at one of our star parties, and we'll look through some of these telescopes that we have here.